All right, chapter 5, curve sketching with extrema and inflection points. So this is what you want to do for our procedure. Now I will tell you the examples we are doing already has f prime and f double prime. They took the derivatives for you. But that's not always going to happen in your homework, okay? So make sure that when we find our relative max and min, we're using the first derivative. And when we find the inflection point of inflection, we use the second derivative, okay? So let's see. Let's go in order. What I want you guys to do is, if you remember, all of these 6 things right here have to deal with our f of x function, okay? So let's look at that right now. Sorry, I dropped my pen, guys. Okay, domain. Domain are all the x values that it happens. So we want to look at what can't happen. What can't happen is a negative under a radical or a 0 in the denominator. But if you look at the denominator right here, any number we square will be a positive number, and when we add 1 will be a positive number. So it won't ever be 0. So the domain for us is all real numbers. So right away, that helps us with our holes in our vertical asymptotes. So that means there are no vertical asymptotes and no holes. And also remember, holes come from where you cross out, and vertical asymptotes come from setting your denominator equal to 0 and solve it. Now if we look at x-intercept comes from the numerator being 0. So what makes the numerator 0? That would be 2x cubed equals 0, and when we solve, we get x equals 0. So x-intercept would be at 0, 0. Now what I want to point out here is this is a cubic, so that means it's an odd intercept. Now why did I say that? It's because that means that it crosses at that x-intercept. It doesn't touch. Remember, if it's even, it touches. The y-intercept is plugging in 0 for x. So when we plug in 0, we get 0 over 0 plus 1. That's 0 over 1, which is 0, which makes sense since our x-intercept is 0, 0. Now, end behavior. Remember the end behavior, we look at the exponents, right? So this is an x cubed, 2x cubed over x squared. Our numerator is larger than our denominator. So if I simplify that, that comes down to 2x. Well, what does 2x look like? 2x looks like that the left is going to negative infinity and the right is going to positive infinity. You don't need to write it with limit notation because the major part of this topic is the graphing. This is what we need to graph. Okay, next step would be a relative max and relative min, right? And if I were to draw this, I can. These come from the first derivative. Now, how can we find these? Well, we take the first derivative, and remember, we find our critical numbers. Our critical numbers are when the derivative does not exist or equals 0. So what values does our first derivative equal 0 or does not exist? Well, let's see, what values would happen here? If we set this top to 0, we would have, this would never become 0, right? Because of positive, but what makes this 0? X equals 0. And our bottom, right, that would be our does not exist. Again, because we're squaring and adding 1 to it, it will never be 0, so we don't have a do not exist. So when we make that number line, the only critical value we're looking at is 0. And when we do that, we have a plus and a minus there, right? But if we look, this is an even. So what do we have to do with even since it's squared? We have to add 2 rows of the same one. So we get plus, plus. So what does that mean? If we're increasing, that means there are no relative max and no relative min. Okay, point of inflection. Point of inflection comes from the second derivative. Again, it's finding the critical number, so where it equals 0 or does not exist. So if we look at the bottom, let's get rid of that does not exist because this would never be 0 yet again. So where it's 0, we look at the top. As you can see, this negative 4x, how can that be 0? Well, that's 0 when x is 0. And where does the x squared minus 3 equal 0? Well, it's positive and negative square root of 3. If you want on the side, I can show you. X squared minus 3 equals 0, and we can solve. Square. And then when you take the square root, don't forget that it's plus or minus. Okay? So now when we do this number line, so we have 0 and plus or minus square root of 3. So when we do this number line, and I'm going to try to squeeze it in right here, guys. I get negative square root of 3, 0, and square root of 3. Okay. Our 0 is only once, and our square root of 3, the plus and minus, is only once. If you do all of that number line, you end up getting positive, negative, positive, negative. Now, the only reason I didn't set up it like this, guys, is I'm running out of room. So if you want to use those each row, go for it. I just wanted to give you the answer right there. Points of inflection are where it changes between positive and negative. Remember, this talks about concave up, concave down. So it's where the concavity changes. So we have a change in concavity at negative square root of 3, at 0, and at square root of 3. Now, points of inflection are coordinate pairs. So what happens is we have to put in these x values to the original problem to get the y values. So what happens is 0, of course, is 0. And if I plug in negative square root of 3, I end up getting negative 3 square root of 3 over 2. If I plug in square root of 3, I get 3 square root of 3 over 2. All right, so how do we graph this? Well, first of all, you want to deal with the things that you know exist. And that is where our original function helps us, okay? So from our original function, I know that I have an x-intercept and y-intercept at 0, 0. Now, really, I know the end behavior over here somewhere goes up and over here goes down. So what I recommend you now plug in is where your relative max, relative min, and your point of inflections are. So we have a point of inflection at 0, 0. We have a point of inflection at negative square root of 3, probably right there. 3 square root of 3, so somewhere down here. And don't forget, this is a sketch, so it is okay to not be exact. Okay, now of course, this looks like a line, but we're not going to do that. Because if we did that, we wouldn't have any concavity. So now I'm actually going to look at the concavity itself. Concavity means, and I'm going to look at 0, 0 first, because I want to look at the middle. So if I look here, I have it going concave down, right by that 0, and concave up on the other side. Now I'm going up to those points because those are points of inflection. That's where our concavity changes. Okay, so down here, now don't forget, this is increasing the whole time. So I can't like make it decrease somewhere. So I want to make this a concave down, but it's still increasing. And what did I do here? Oh, this is not concave down. That's my mistake, guys. It's concave up, right? So I need to go like this. Sorry, concave up. Where this one's going to be concave down. So this one's going to go down here. Something like that. Weird graph. Hopefully the other ones are a little bit better. And that's all we're doing. We're sketching. It does not have to be perfect. Okay, so again, I'm going to look at the function first. Now, domain, we need to find out where it doesn't exist, right? Or where it can't happen. But if you look at this, we need to factor. When you factor, you find out that this is x minus 1 squared. So domain, what can't it be? It can't be 1. So the question is that 1 going to be a vertical asymptote or is it going to be a hole? Well, it doesn't cross out, so it must be a vertical asymptote. So we have a vertical asymptote at x equals 1. What I also want you to keep in mind is that it is squared, so it is even. And if you remember, even means that it goes in the same direction. Now, at this moment, we don't know if they're both going up or both going down. So be careful at that. No holes, because we didn't cross anything out. X-intercept. What makes the numerator 0? That would be 2/3. And that's to the first, so it's odd. What does that mean again? It means it crosses the x-axis. Y-intercept is when we plug in 0. When you plug in 0, we get -2/1. So 0, -2. Okay, there is our function. Now let's look at our derivative here. Our first derivative, and look at our critical values, critical numbers. So we have a critical value at 1/3, right? Because that's what makes it 0. And don't forget, we have that vertical asymptote, and that needs to be put on our number line at 1. Okay, so when I make that number line, I have 1/3. I want to keep in mind that this is a vertical asymptote at 1. Okay, and now I'm going to make our number line. So I go negative, positive, positive, negative, negative, positive, but there's one extra thing you guys have to keep in mind. We need a row of negatives. Why? Because this function is negative. So we have a negative, positive, negative. Okay, so it looks like we have a decreasing to increasing, right, at 1/3. So that means a min at 1/3. And of course, we need to plug back into the original to know what the y value is. And I just noticed, guys, that I forgot the end behavior, so we'll do that in a minute. Relative max. Even though you think there's a relative max here, as you can see, I indicated it as a vertical asymptote because can we have a point at a vertical asymptote? No. So there is no relative max. Let's go back to that end behavior. Okay, end behavior, we're looking at a 3x over an x squared. What does it mean when the denominator has bigger exponent than the numerator? It means that there is a horizontal asymptote at y equals 0. Okay, let's look at the second derivative for the point of inflection. What's our critical numbers? Well, of course, we have a critical number at what makes the numerator 0? 0. And we have a vertical asymptote still that we have to keep in mind at 1. Okay. So 0 and 1. Now let's look at this. This is even, right? So we need to do the 1 twice. Okay, so I'm going to keep that in mind. So let's do the 0. The 0 is negative, positive, positive. That's the row for the 0. And the row for the 1 is negative, negative, positive. And I have to do that twice because it's an even exponent. So we end up with negative, positive, positive. Keep in mind that this is a vertical asymptote. So that means we only have a point of inflection at 0. And then when we plug that back in, it's at negative 2. All right, let's see if this graph comes out a little bit better than the other one. So I'm going to do all my points first. So I have an x-intercept at 2/3, 0. So that's close to 1, right? I have a y-intercept at 0, negative 2. Okay, I have a relative min at 1/3, negative, so somewhere down here, right? Okay, now I also want you guys to keep in mind, we want to do our vertical asymptote, which is at 1. And we have a horizontal asymptote at 0. All right, so what do you think is going to happen here? Well, if either you can look at your concavity and everything, as you can see, we're concave up between 0 and it looks like we're just concave up all that way there. So I'm going to go concave up here. Now, this x-intercept is odd, so it goes through, which is nice because we just continue following that vertical asymptote. Well, since that vertical asymptote is even, that means on this side it's going up. Now, as you can see on the other side of this vertical asymptote, we're still concave up, but what I want you to keep in mind is the end of it is at our horizontal asymptote. We do not cross the x-axis because that was our only x-intercept, right? So there we go on that side. So what's happening over here? Well, we have to go concave down after 0. So concave down. So see how I'm making my frown there? Now again, same thing on this end. I can't cross the x-axis because that was the only x-intercept, but I can follow this horizontal asymptote. What's going on, huh? Okay, last one. Look at what we have. Let's look at our domain first. What can't x be? Well, this can't be 0, right? So what makes it 0? Well, again, I'm squaring and adding 2 and then taking the square root. I will never get 0 in that case. And whatever number I put in for x, I'm squaring it, so under the square root will never be negative. So it's all reals. Which means if it's all reals, we have no vertical asymptotes and no holes. Remember, holes are where you cross off. Now, x-intercept, what makes the numerator 0? Well, 0. And that's for the first. So we have an odd, which means it crosses. Okay. Well, of course, if the x-intercept is 0, so is the y, but we can double check. Right? You plug in 0 for x's, you get 0 over the square root of 2, which is still 0. As to end behavior, this one's going to be a little bit trickier. Remember, end behavior is from our exponents, right? So if I look at the highest exponents, I have x over the square root of x squared. Well, if you think about that, that means we have x over, and this is where we get to the absolute value of x. So as we go left, so negative infinity, right, we would get a negative over a positive, which is a negative, and we take the coefficient in front. Coefficient in front is 1. So our left side is going toward -1. And our right side, because when we plug in infinity, we get a positive over a positive, which is positive. Again, coefficient in front, so it's going to be a +1. This is going back a little bit. All right, let's look at our relative max and mins. So critical values for our derivative. Well, what makes the numerator 0? That would be nothing. What makes the bottom 0? Nothing. So no critical values. And what happens is that just means that everything is positive. Okay. So the whole thing is increasing. If the whole thing is increasing, we have no relative maxes and mins. Point of inflection, look at our second derivative. So our critical numbers, well, what makes the top 0? That would be 0. What makes the bottom 0? It can't be 0 because of the x squared in there. So I have 0. So that would be a negative positive, but don't forget this function is negative. So negative, negative, right? Row of negatives. So we have positive, negative. Okay, so that means we do have a point of inflection at 0. Remember that changes concavity. So 0, and then plug back in, we get 0 over 0, or 0 over square root of 2, which is 0. Okay, let's graph it. Okay, do all my points first. So I have an x-intercept, y-intercept, and a point of inflection, which are the same. There are no vertical asymptotes, but there is an end behavior. So at the left, we have a -1, and I'm only going to do the end of it, not the middle, okay? At the right, we have 1. Remember, it gets really close. Now, what I would do with this then is look at that point of inflection. That means we have a concave up on this side, concave up, and this side we have a concave down. So see how I make little indications of where it's going. Now, if I look at that horizontal asymptote, now I can see, hey, I'm just going to get close and keep going. Same thing here. I'm going to get close and keep going. Did I do it? Concave up, concave down. Is the whole thing increasing? Yes, it is. Some of these might take a little bit of time. And don't forget, many of these problems, you might have to find the first derivative and then find the second. Okay, good luck.